Hey everybody, this video is going to be pretty important for us. It's going to try to tie the arithmetic sequence stuff we've been working on to your work with y equals mx plus b that you did last year. And I want to address the issue with the starting points when we have sequences and context. But this video won't do the geometric because a geometric sequence is not related to a linear function, because they're not. So let me get started, and I've got some notes written for you, and I think they look a little complicated at first, but I'll explain it. Okay, so here's the beginning, and this is just has to be said formally. It doesn't mean that we have to spend an hour on it or anything like that. Or I'm just saying, remember y equals mx plus b. Okay, this is that function you've dealt with for all last year. And remember, we have function notation that replaces y with f of x. So it can also be written using f of x equals mx plus b. Recently, we also learned that we can use the point-slope formula that we see right here to write equations of lines. All right, so what I've done is I replaced y here with f of x. Remember, y1 and x1 are just parts of an ordered pair. And when I do that substitution, replacing y with f of x, we get f of x minus y1 equals m times x minus x1. In this section, we're going to compare and contrast how this equation is related. Now, look at your formula for the nth term of an arithmetic sequence formula. F of n equals f of 1 plus d times n minus 1. Now, I want to show you what I've done. I'm not getting super deep in any kind of algebra or anything like that right now. I just wanted to, I want to show you how I came up with that formula. It's really, really simple. So I started by saying, look, we've got this, so far, this is my point-slope formula, right? And all I've done is replace y with f of x, just like we said we could do with f of x notation. So then I want to add this to both sides of my equation. We'll add y1 over here. Remember, we can do that as long as we add the same thing to both sides of an equation. It'll remain a true statement. So I'm going to put this as y1 plus m times x minus x1. Oops. Now, here's what I wanted to show you. I wanted to compare this to this other function we've been working with, the sequence. And what is y1? Well, in sequence world, that's f of 1. So it's the first term, right? What is m? That's the slope in your formula. Well, over here in sequence world, that's a common difference. Yeah, it's still a rate of change, right? And over here you'd have n, not x, because remember your independent variable in the sequence world is n, and your first term always is 1. X sub 1 is 1. All right, so this is the point-slope formula, but it's sequences. I know that might sound obscure and kind of just not even a big deal to you right now, and I do get that, okay? But what I want to do is show you where it can come in handy for us. And the next videos are about a minute or two long. It won't be really long, where I'll show you how this really makes a difference when we're dealing with a certain context, okay? All right, so let me come down here. What I've written so far in here is I made a table. I said, suppose we had a function y, so this is a function of x, all real numbers, although I'm using the same numbers in the table. And if I told you to write an equation of a line for this thing, you would have to find the slope. Now we're looking at y equals mx plus b side over here, right? And we would say, okay, I would calculate a slope using my point-slope formula that I've changed slightly by putting y1 on this side. I'd have 7 plus 3 times x minus 1, because I'm choosing this point for x1, y1, okay? That's what I did. Working with sequences, we've done this so many times together. I really feel like it's just hopefully you're starting to get it second nature here. You can see your sequence going up 1, 2, 3, 4. It's got a common difference of 3. I show that there. And if we plug it in, look what you get. I mean, these are the same thing. They are the same thing. Now, when you simplify it, now all I did to get this right here is I distributed that 3. 3n minus 3. And you know what? I'll show that because I got folks that keep on saying I'm losing on when I'm doing that. So let's just do that one more time together. Maybe this time you can follow along. Okay, so I have f of n equals 7 plus 3 times n minus 1. And the other one I have f of x equals 7 plus 3. And I'm not going to do both because they're exactly the same. But when you distribute that 3, and I'm going to show it with some red arrows because I've been saying it over and over. Maybe we need to do some practice on distributing. We go there, and we go there. And when we do that, we're multiplying, guys. We're multiplying. I can't say this enough times. And we get, copy this down, you get 3n minus 3. So f of n is actually 3n, and we're combining like terms, this one and this one, to get plus 4. All right, that's how we got that equation, and we need to get in the habit of cleaning things up that way. All right, so this is y equals mx plus b. That's a y-intercept. Now, that one, we wouldn't say the sequence has a y-intercept, and I'm going to show you why. Remember, because they start with n is 1, 2, 3, 4. If n is 1, we get 7, right? Over here, if we can have 0 for x. If x is 0, we get y-intercept of 4, right? But we need to learn that if a sequence has a context, that's kind of why I'm doing this. It's okay to have an initial amount or a starting point like that. So what I've done, this would be the graph of your sequence, right? It would just be these dots right here. That's all that sequence is. There is nothing in between them. You cannot connect these dots. It's called a discrete function because n is 1, 2, 3, 4, 5, and so on. There is nothing in between them. All right? To contrast that, there's your y equals 3x plus 4. Now, it's a solid line. There's infinitely many points in between 1 and 2. There's 1.1, 1.12, 1.112. Everything that you can imagine that lives between 1 and 2 is there. With the discrete function, nothing's there between them, okay? So the continuous function has this solid line. Your discrete function would just be these dots. All right. Let's see what else we got to talk about. And I'll put those graphs in here so you can see it. So there is a difference in these functions. There is. But that's why I say they're close cousins. I've always described it that way. I think it's helpful. I'm going to show you how you can back a sequence up depending on the context, if it's a word problem, where you might consider it having sort of a y-intercept. So that's in the next video, and I'll get right into that. That one won't be as long as this one. So thanks for checking this out, and I will see you in the next